Physical properties of alloalkanes and alloarenes. Okay. Generally, in these physical properties, we are going to be learn solubility of the alloalkanes and alloarenes and their physical status. That means, are they solids or liquid or gases? Next, we studied in the physical property is the okay boiling point of this alloalkanes and alloarenes. Next, density we can study. Okay. Next, solubility we can study in the physical properties. What we are going to be studied in the physical property? We will study their physical status. That means, are they gases or liquid or solids? Okay. Next, we studies their boiling point. Okay, their boiling point. Second, we study the density of alloalkanes. Okay. Next, we study the solubility of this alloalkanes. Like that. Okay, in the physical property we can study. Okay. First point I am saying that one, the physical status of the alloalkanes and alloarenes. Okay. So lower alloalkanes are gases in the nature. Okay. Lower alloalkanes are gases in the nature. As molecular weight increases, gases will converted into liquid state. Still, large molecular weight of the alloalkanes and alloarenes are solid in the nature. Okay. This point is applicable to any organic compounds. Any organic compounds. What I am saying that one, lower alkyl containing any hydrocarbons are gases. Okay. As alkyl group increases, it is converted into liquid state. As more alkyl group increases added, it is converted into solid state. That means they are the solids. Okay. So what I am saying that one, lower alloalkanes are gases in the nature. Middle alkyl containing halogen compounds are liquid in the status, and alloarenes are solid in the nature. Okay. Next point, the boiling point. The boiling point of the alloalkanes and alloarenes are greater than hydrocarbons. What I am saying that one, boiling point of the alloalkanes and alloarenes are greater than hydrocarbon. What are the hydrocarbons? Alkanes, alkenes and alkynes, and aromatic hydrocarbon is benzene. Compared to with them, this alloalkanes, alloarenes boiling point is more. Okay. Next point. So this boiling point will increases. As molecular weight increases. Okay. This point also applicable to any organic compounds. Okay. In the coming days, you are going to be learn so many organic functionalizations. The same thing will be applicable to all functional group. As boiling point increases, as molecular weight increases. Boiling point increases as molecular weight increases. Okay. For same alkyl group, where is same alkyl group or is called, for example, methyl or ethyl, methyl iodide, methyl bromide, methyl chloride, methyl fluoride. For same alkyl group, as the molecular weight of the halogen increases, the boiling point is increases. Okay, we know that one from top to bottom, molecular weight is increasing. From fluorine, bromine, iodine. Iodine is more molecular weight compared to fluorine. Therefore, alkyl iodide is having more boiling point than the alkyl fluoride. In same aromatic allo compounds also, that means alloarenes also, because the benzene ring is common in all alloarenes. Okay, only molecular weight of the halogen increases. Okay, that's why what I am saying that one, boiling point increases as molecular weight increases. Okay. Next point, for same halogen, boiling point increases as alkyl group increases. Okay, for same halogens. Okay, here the what I say that one here, so different halogens. Okay, halogen molecular weight increases, the boiling point increases. Okay, here for same halogen, boiling point increases as alkyl group increases, vice versa. Vice versa. That means, okay, halogen atom is constant. As alkyl group increases, boiling point increases. As alkyl group decreases, the boiling point is decreases. That means vice versa means lower alkyl group is having lower boiling point, higher alkyl group is having higher boiling point. The condition is halogen atom must be the same. Halogen atom must be the same. Here chlorine, ethyl chloride and propyl chloride. Okay, all halogen atoms are same. That is the chlorine here, chlorine is here, chlorine here, but alkyl group is changed. Here is methyl, 1 carbon. Here is ethyl, 2 carbon. Here is propyl, 3 carbon. So boiling point increases as molecular weight increases. Boiling point increases. Okay. Next point here. Okay, same point, similar alkyls, similar halogens. Okay, for same halogen, as branches increases, boiling point decreases. As branches increases, boiling point decreases. Okay, this point already covered in hydrocarbon chapters. Hydrocarbon chapters. Okay, so boiling point, this is the N-chloropropane. Okay, normal chloropropane, and this isopropyl chloride. Okay, so this is a branched haloalkanes. It's the normal haloalkanes. What I say that one? As branches increases, boiling point decreases. Therefore, compared to iso, that means branches, okay, boiling point is lower than the normal haloalkanes. Because as branches increases, van der Waal attraction forces among the atom is decreases. Okay, as branches increases, that means the atoms may not be packed properly. Whenever the linears or whenever the normal, they will pack very well. When they are packed well, there is more van der Waal attraction forces between the molecules. As van der Waal attraction forces more, the boiling point will increases more. But whenever the branches are there, the packing is not much. Okay, packing efficiency or packing of the two molecules will not be there properly. So if there is no packing properly, there is no van der Waal attraction forces between the two molecules. If there is no van der Waal attraction among the molecules, they will not hold strongly, so they will boil off very low temperature. That's why the boiling point will decreases. Okay. Next, come to the solubility. Haloalkanes are partially soluble in waters. Okay, haloalkanes are partially soluble in water. That means, okay, they will not soluble completely. Okay, partially soluble in water, and haloarenes are insoluble in water. Haloarenes are insoluble in water because the benzene ring is there. Benzene ring is the hydrophobic nature. As carbon chain increases, hydrophobic nature increases. Hydrophobic nature increases means the solubility will decreases. Okay, and what I say that one, haloalkanes are partially soluble in water. Haloarenes are insoluble in water. Both the haloalkanes and haloarenes are highly soluble in organic solvents like carbon tetrachloride and chloroform. Okay, so what I said that one, they are partially soluble and insoluble in water. Okay, but they are highly soluble in carbon tetrachloride and chloroform. Okay, that is because of like dissolves like. That means organic compounds will soluble in organic solvents only. Organic solvent soluble in only in organic solvent. Inorganic solvent will soluble in that means aqueous solvent will soluble in aqueous solvent only. That is called like dissolves like. Okay, these are the physical properties of alloalkanes and alloarenes. First we study the physical status. In the physical status, lower alloalkanes are gases in the nature, and molecular weight increases, the converted into liquid state. As the molecular weight increases, they are the solid state. Okay, and we studied the boiling point. The boiling point of alloalkanes and alloarenes are greater than the hydrocarbon chains. This boiling point increases as molecular weight increases. Boiling point increases as molecular weight increases. Okay, this is the example. Okay, next point is for same halogen compound, as alkyl group increases, the boiling point increases, vice versa. That means as alkyl group decreases, the boiling point decreases. As the alkyl group increases, the boiling point increases. Condition is the halogen atom must be the same. Halogen atom must be the same. Okay. Next point, as compared to normal haloalkanes, branches. The next one point is branches alloalkanes are low boiling point compared to normal alloalkanes because of the decrease in the van der Waals attraction forces between the atoms when the branches increases. Okay. Finally, come to the solubility. Solubility also, this alloalkanes and alloarenes are less soluble or partially soluble in water. Okay, partially soluble in water, and alloarenes are insoluble in water, and they are highly soluble in organic solvents like carbon tetrachloride and chloroform. In case of density also increases as molecular weight of the halogen increases. Okay, these are the physical properties. These are the physical properties of alloalkanes and alloarenes. Next one is the chemical properties. In this one, first point is discussion point is nature of CX bond. Okay, what is the CX bond and what is this one? This is the carbon and halogens, which already we studied. Alloalkanes. The general formula of alloalkanes is CX. Where is the carbon? X is the halogen atom. Halogen atoms are fluorine, bromine, iodine. Okay, so we are going to be seeing what is the nature of this CX bond. What is the nature of CX bond? Okay, so if I write the structure of the CX bond, so this is the carbon is the tetravalency. Around the carbon, 4 bonds are there. 1, 2, 3. Okay, 4, and is attached to the halogen atoms. It is attached to the halogen atoms. Okay, so we know that one. Okay, carbon and halogens. We know compared to carbon, halogen atom is more electronegative. That means carbon atom is less electronegative. Halogen atom is more electronegative. So as the more electronegative nature of the halogen atom, it will pulls electron from the carbon atom towards it. Okay, what is doing due to high electronegativity nature of the halogen atom. Okay, halogen atom, it will pulls the electron towards it from the carbon. As that is called inductive effect. Due to inductive effect, electrons are moved from carbon to halogen atoms. As electrons move from carbon to halogen atom, the halogen atom electron density is increases. That is indicated by delta minus. As electrons are deficient at carbon, so that is indicated by delta plus. That means, okay, due to inductive effect or high electronegativity nature of the halogen atom, carbon is getting partially positive charge. Halogen atom is getting partially negative charge. Why? Because of due to electronegativity difference between carbon and halogen atoms. That is due to the electronegativity difference between carbon and halogen atom. So halogen atom will take the electron from the carbon due to its more electronegativity nature. Okay, yes, this partially positive charge is responsible for this halogen atoms to undergo the chemical reaction. For this, undergo the chemical reactions. Okay, this is the X minus and this C plus, and the carbon positive charge is generating. That's why it is it is a place where the nucleophile can attack. That's why halogen atoms will undergo the nucleophilic substitution reactions. Okay, what I'm saying that one. Alloalkanes are undergoing nucleophilic substitution reaction. Why it is undergoing nucleophilic substitution reaction? Because a carbon positive charge is generated. This positive charge can accommodate only another negative charge. Or negative parts. That's why another negative part is called nucleophile. So this is called nucleophilic substitution reactions. Okay, what I'm saying that one? Alloalkanes are undergoing nucleophilic substitution reaction. What is the nucleophilic substitution reaction? Here in alloalkanes, X is also a nucleophile. On halogen atoms, how many? 3 unpaired of electrons will be there. Okay, 3 halogen atoms. Okay, seventh group. Therefore, 1 electron is involved the bond with carbon atom. Another 6 electrons. That means 3 electron pairs are available around the halogen atoms. Therefore, it is also a nucleophile. Nucleophile is substituted with another nucleophile. To give the nucleophilic substituted product. That's why the chemical reactions in which one nucleophile is substituted by another nucleophile is called nucleophilic substitution reaction. The chemical reactions or the organic chemical reaction in which one nucleophile is substituted by another nucleophile is called nucleophilic substitution reaction. Here one nucleophile is X, that is halogen atom. Another nucleophile is represented by Nu. Nu is nucleophile. Okay, abbreviation and Nu is the nucleophile is substituted to the halogen atoms will give the CNU plus X minus. Okay, this is the nucleophilic substitution reactions. These are the example for the halogen atoms where it will undergo nucleophilic substitution reaction. Here these are all the nucleophile in which X atom, X is the nucleophile, is substituted by another nucleophile. Okay, for example, in first case sodium hydroxide. Na plus OH minus. OH minus is a nucleophile. Here OH minus will attack on the halogen atoms, or halogen atom is replaced or substituted by the OH atom. So we will give ROS, that is alcohol, and NaS. Okay. Next one water. Will dissociate into H plus and OH minus. Again OH minus is a nucleophile. This nucleophile is substituted with this nucleophile to give again alcohol and HS. Okay. This is the sodium alkoxide. NaOR minus. OR minus is a nucleophile. This OR minus, nucleophile or alkoxide is substituted with this halogen atom. Will give the ethers. Okay. Ether, and the product side product is NaX. Okay. Ammonia NH3. Ammonia is the fifth group element. 15th group element or 5th group element. Around the nitrogen, three bonds are there already. CH3. Okay. And one lone pair is there on the nitrogen. Therefore, ammonia will act as a nucleophile. This nucleophile also substituted with halogen atoms will give the amines. It is a primary amine, 1 degree amine. It is a 1 degree amine. 1 degree amine. Second one is again this primary amine or 1 degree amine reacted with the halogen atoms. Halogen atoms. This haloalkanes will give the 2 degree amines. 2 degree amines. Okay, because 1 degree amine also a nucleophile. 1 degree amine also a nucleophile. This again replaced with the halogen atoms. Okay, and second one is the 2 degree amine. Again this 2 degree amines again replaced with these halogen atoms will give the 3 degree amines. 3 degree amines. Okay, next one is potassium cyanide. Potassium cyanide. Okay, potassium cyanide will give the alkyl cyanide. Alkyl cyanide and silver cyanide will give the alkyl isocyanide. Alkyl isocyanide. Okay, these two are called ambidentate ligands. Ambidentate ligands. I will give the example for this one too. Ambidentate ligands means the ligand in which two nucleophilic centers are present. The ligands in which the two nucleophilic centers are present, that nucleophiles are called ambidentate ligands. Ambidentate ligands. Okay. So here cyanide, carbon in this one, carbon is coordinated to the alkyl group. This is the one nucleophile center, and silver cyanide, nitrogen is attached to the alkyl group. Nitrogen is attached here. It's a one nucleophile center, it's a two nucleophile center, but one molecule. Okay, one molecule. Cyanide is a one molecule. It can attack by the carbon as also attacked by the nitrogen. The ligand which can coordinate to the alkyl group by the two centers, two nucleophilic centers are called ambidentate ligands. Okay, similar example, RNO2. Okay, RNO2, alkyl nitride, RNO2 and alkyl ONO. Okay, so that means alkyl nitrile is also a ambidentate ligand. Ambidentate ligands. Okay, here alkyl group is attached by the nitrogen atom, same formula. Okay, but alkyl group here attached by the oxygen. This type of ligands are called ambidentate ligands. Ambidentate ligands. This is the important pattern. Okay, important point is ambidentate ligand. That means the ligands which possess two nucleophilic centers. The ligands which possess the two nucleophilic centers are called ambidentate ligands. Okay, the ligands which possess two nucleophilic centers are called ambidentate ligand. Example are cyanide and alkyl nitrile. Okay, so this is alkyl nitrile, this is alkyl nitrito. Okay, O is attached to alkyl group, here nitrogen is attached to alkyl group. Okay, so the ligand in which two nucleophilic centers are present, they are called ambidentate ligands. Ambidentate ligands. These are the physical properties and the chemical properties. The chemical properties we learned, the alloalkanes are undergoing the nucleophilic substitution reaction. Nucleophilic substitution reaction, because the halogen atom, in the halogen atom, the carbon is having partially positive charge, halogen atom is having partially negative charge. Therefore, one nucleophile is substituted by another nucleophile. That's why it is called nucleophilic substitution reaction. We should remember at this point, we must be remember, alloalkanes are undergoing nucleophilic substitution reaction. Alloalkanes are undergoing nucleophilic substitution reactions.